In the last part of today's module, we're going to look at calculations of pH from weak bases. So bases, they react with water to produce hydroxide, right? We looked at ammonia behaving like a base. It's a proton acceptor. It accepts a proton from water. Water is the acid in this reaction, and that makes the conjugate acid ammonium and the conjugate base hydroxide. We can write the same equilibrium expressions for bases reacting in water that we can write for acids reacting in water. We can come up with the same equilibrium expressions. So for a generic base B reacting with water to form its conjugate acid and the conjugate base hydroxide, right, here's our generic base. In this reaction, water is the acid. I'm going to form the conjugate acid, HB, and the conjugate base hydroxide. That equilibrium expression is no longer the Ka. Ka is for acids, Kb is for bases, but it's the same thing. It's still our concentration of products over our concentration of our reactants, and Kb is the base dissociation constant. So for this generic base, my equilibrium expression would be what's the concentration of HB, my conjugate acid, times the concentration of the conjugate base, hydroxide, all over the initial concentration of my base. Because we're going to ignore water. Water's a liquid. We're only going to focus on things that are aqueous in solution for these equilibria. And much like our magnitude of Ka and what does that mean about the strength of the acid, right? As the value of Kb increases, so does the strength of the base. And again, we could memorize that statement, or we could just think about how we calculate Kb. We calculate Kb as the concentration of the conjugate acid times the conjugate base over the concentration of the base. How do I get a larger value of Kb? By having that base ionize to a larger extent, forming more products. A larger concentration of products over a smaller concentration of reactants will give me a greater value of Kb, and that's associated with a stronger base. I'll have a higher concentration of hydroxide in solution. So again, we can look at the Kb values for a series of bases. And again, the important trend is that the larger the value of Kb, the stronger the base. The smaller the value of Kb, the weaker the base. And so of the bases listed, right, the largest Kb would be from methylamine. So that would be the strongest base of this series. And the weakest base of this series would be pyridine. It's the smallest value of Kb. We're going to take a look at ammonia and calculate the pH of a solution of ammonia using the Kb of ammonia. So the question here is how to determine the pH of a 0.15 molar solution of ammonia. Given that ammonia reacts with water to form ammonium and hydroxide, and in this case we know the Kb for this reaction. I know the base dissociation constant. That expression, products over reactants, so the products are the concentration of ammonium times the concentration of hydroxide all over the concentration of ammonia. The water is ignored because it's a liquid. So let's think. I want to know the pH of this solution. Right now, all I know is the Kb and the ammonia concentration. Eventually, I need to find hydronium concentration so I can take the negative log of that and find the pH. So we need to find ammonium concentration and the hydroxide concentration to be able to find the pH of this solution. So much like the last time, the ammonium concentration, the hydroxide concentration, based on the balanced chemical equation, they are formed in the same amounts. So I should have equal concentrations of ammonium and hydroxide. Both of those should be X, and they should be equal to each other just based on the balanced chemical equation. I can make the same assumption I did before in that because this is a weak base, it only partially ionizes in solution, and my initial concentration will be very similar to my equilibrium concentration. And I could ignore any changes in that concentration. This will simplify the calculation. So we know the Kb and we know the concentration of ammonia, and we've decided to call ammonium and hydroxide both X. So Kb equals the concentration of ammonium, which is X, times the concentration of hydroxide, which is X, all over our concentration of ammonia, 0.15. So multiply the 0.15 across, and I'm left with X squared equals 2.7 times 10 to the minus 6. So I'm going to take the square root of both sides to get X by itself, and I'm left with X equals 1.6 times 10 to the minus 3. And again, people get caught up in the calculation. They forget what is X. So X equals my concentration of hydroxide. So this calculation is a little bit different than the calculation we did from Ka to pH, because now I know the hydroxide calculation. The next step, I can find pOH, and then I can find pH. So I've got one more step in this calculation than I did in the previous example. So remember, pOH equals the negative log of hydroxide concentration, and that's what I have. I have hydroxide concentration, so my pOH equals the negative log of 1.6 times 10 to the minus 3. So my pOH of this solution is 2.78. The last thing I know that pH plus pOH equals 14, because ultimately we want to find the pH of this solution. So I know that pH equals 14 minus the pOH. So the pH of this solution equals 14 minus 2.78. The pH of this solution is 11.22. Always ask yourself, does this number make sense? Yes, this makes sense because I'm calculating the pH of a solution of a base. Ammonia is a base, and I calculated a pH of 11.2, which is a basic pH. Here's one final relationship to consider, the relationship between Ka and Kb, the acid and base dissociation constant. And we're going to look at a conjugate acid-base pair for this relationship. So first we need to write what is the Ka and the Kb for both of these reactions. So the first reaction is ammonium behaving like an acid. So I'm going to start with the Ka, the acid dissociation constant of ammonium. I'm going to ignore water as a liquid. That is the concentration of ammonia times the concentration of hydronium all over the concentration of ammonium. The Kb for ammonia acting like a base is the concentration of ammonium, NH4 plus, times the concentration of hydroxide all over the concentration of ammonia. Now we're going to take a look at what happens when you add these reactions together, and then take a look at what that means for the relationship between Ka and Kb for a conjugate acid-base pair. Right, if I add these two reactions together, ammonium behaving like an acid, ammonia behaving like a base, if it's on the left and the right side of the equation, it cancels out. So the ammonia cancels out, the ammonium cancels out, and I'm left with water plus water yields hydronium and hydroxide. So what does that mean? That means, right, the product, the sum of these two reactions, that means the product of Ka and Kb is a relationship we're already familiar with. So let's multiply Ka and Kb together to see what that results in. Right, the Ka was concentration of hydronium times the concentration of ammonia all over the concentration of ammonium. So multiplying Ka times Kb, ammonium times the concentration of hydroxide all over the concentration of ammonia. We see that the ammonia cancels out, the ammonium cancels out, and we are left with what is hydronium concentration times the concentration of hydroxide, also known as our Kw. So for any conjugate acid-base pair, Ka times Kb equals Kw. We've got one last relationship. So now if we know the value of Ka, we can find the value of Kb for that conjugate base because Ka times Kb equals Kw for a conjugate acid-base pair. So for any conjugate acid-base pair, Ka times Kb will equal Kw. So if we know the value of Ka, we can find the value of Kb for the conjugate base of that acid, or vice versa. And that also helps understand the relationship that we were talking about earlier for what does the value of Ka mean for the strength of the acid, right? So the larger the value of Ka, the stronger the acid. And the stronger the acid, the weaker the conjugate base. And so what do we notice over here? Numbers that have very large Ka have very small Kb. So as my acid gets stronger and stronger and stronger, my base gets weaker and weaker and weaker, right? Because larger Kb values correspond to a stronger base in that case. So we have an inverse relationship, right? Strong acids have very weak conjugate bases, and as the strength of that acid decreases, the strength of the conjugate base increases. So in summary, what's important from today, understand where Ka comes from, what Ka means, what that means with respect to acid strength. The larger the Ka, the stronger the acid. Understand how to determine Ka from pH or pH from Ka, those initial calculations we did, and understand the same information for Kb. So the larger the value of Kb, the stronger the base, and be able to do the same calculations. Can you go from Kb to pH, or could you go from pH to a Kb value? You should be able to do those calculations both directions. Monday, we're going to look at the common ion effect and buffers, and we're going to get to look into the solubility and solubility equilibria and the last equilibria that we're going to look at.